Good day everyone, I'm Cjpj and I'm going to discuss the Newton's three law of motion. But first let us discuss who is Newton or Isaac Newton. Sir Isaac Newton was an English mathematician, physicist, astronomer, alchemist, theologian, and author widely recognized as one of the greatest mathematicians and physicists of all time and among the most influential scientists. He was a key figure in the philosophical revolution known as Enlightenment. Sir Isaac Newton changed the way we understand the universe. In his own lifetime, he discovered the law of gravity and motion and invented calculus. He helped to shape our rational worldview. So let us proceed in the three law of motion. The first law of motion is the law of inertia. Galileo said that the velocity is not necessarily zero if there is no force. It is acceleration, which is zero if there is no force. The idea was restated by Newton's first law of motion, sometimes called the law of inertia. Inertia is the property of a body that tends to preserve the body states of rest. When it is at rest, to maintain a body's motion. When it's in motion, the mass of body is a measure of its inertia. Example: consider a passenger standing on a bus that is running at a constant speed along a straight highway. When the driver suddenly steps on the brakes, the passenger is thrown forward. According to Newton's first law of motion, the passenger maintains his state constant speed unless acted upon by external force. To avoid being thrown forward, the passenger tries to grasp a part of the bus to hold him back. We have two parts of Newton's first law of motion. The first is body at rest. Let us use an object lying on a table as an example. According to the first law of motion, this object will remain at rest. This state of rest can only be changed by applying an external force on the body, such that it is a net force. The body is acted upon by two forces as it lies on the table. These are its weights and upward reaction exerted by the table. But these two forces alone have a zero resultant, which means that there is zero net force on the object. The law implies that the smallest net force on the object will move it. Second is body in motion. As for the second part of Newton's first law of motion, consider a body in a motion. This law says that the body will remain in uniform motion along a straight line. This means that it will move at a constant speed in a fixed direction, unless it is acted upon by a net external force. The state of uniform motion can change in one of the three ways listed below. First is the speed is changed, but the direction of the velocity remains constant. The direction of the velocity is changed, while the speed remains constant. And third is both the magnitude and the direction of the velocity are changed. So remember in the first law of motion that the law of inertia is a body at rest proceeds in its states of rest, and a body in motion remains in constant motion along a straight line unless acted upon by an external force. And that is the first law of motion.
Newton's second law of motion, law of mass and acceleration. The second of Newton's three laws of motion is also known as the law of mass and acceleration. The equation F equal ma is probably the most used equation in mechanics. It states that the net force on the body is equal to the mass multiplied by the acceleration. The equation is valid provided proper units are used for the mass and force, and also in acceleration. Both sides of the equation involves vector quantities. It is implied that they must have the same direction, wherein the acceleration is the same direction as the applied force. Since the acceleration is in the same direction as the change in velocity, It follows that the change in velocity due to applied force is also in the same direction as the force. The equation A is equal to F over m says that the acceleration produced is proportional to the net force and inversely proportional to the mass. It can also be written as m is equal to F over A. This equation says that the mass of the body is the ratio of the applied force to the corresponding acceleration. This is also the definition of inertia mass in terms of the two quantities that can be measured. If the body is acted upon by two or more forces, what will be its acceleration? The second law says that the acceleration is in the same direction as the net force. By net force, we mean the resultant of all the forces acting on the body. The figure above shows a body, a mass, acted upon by three forces. The resultant of these forces is the net force on the body, and the acceleration produced will be along the direction of this resultant. Remember in the second law of motion that a body's acceleration is directly proportional to the force exerted on it and is the same direction as the force. Newton's third law of motion. Newton's first two laws of motion refer to single bodies. These two laws are laws of motion. Newton's third is not a law of motion but a law of forces. Newton's third law of motion posits that for every force applied, there is always an equal and opposite direction. Or if one body exerts a force on another, the second body exerts an equal and opposite force on the first. It is not possible to exert a force on a body without a reaction, and the reaction exerted by the body is exactly equal to the force being applied to the body, neither more nor less. It must be kept in the mind in all these examples that the action and reaction forces are applied to different bodies. Take a look in this picture. Figure A. A block is placed on the tabletop. Two equal and opposite forces are shown, F and negative F. These two forces are exerted by the block and the table on each other. What the action is and what the reaction depends upon which body is being considered. If we take the tabletop as the body, then F is the action and the negative F the reaction. The action is the force on the body under consideration, while the reaction is the force by the body on some other body. In figure B, a hammer is driving a peg into the ground. The two bodies are in contact only during a short interval, and both of them may be moving together. At any instant during a short interval of contact, the action and reaction are equal, even if the peg is being driven into the ground. If the hammer is taken as the body, the action is negative F, and the reaction by the hammer is positive F. On the other hand, if the peg is taken as the body, the action on its F and the reaction by it is negative F. In figure C, a terrestrial body is falling toward the Earth's surface. When the body falls, it is being attracted by the Earth, or it is being pulled by the Earth. Since we cannot see the motion of the Earth, the possibility of a force acting on the Earth does not occur to us. Figure D, a man is leaning against a wall. The action on the wall is force F, and the reaction by the wall is then force negative F. The reaction of the wall can be only as much as the force applied to it. It seems strange that the wall is pushing the man, although we see the man pushing. Figure E, two magnets with their north poles are facing each other. In magnetism, like poles repel each other. The repulsive force exerted by one magnet on the other is equal and opposite to the repulsive force exerted by the second magnet on the first. This is true even if one magnet is stronger than the other. In figure F, the third law is applied on a large scale to the Sun-Earth system. It was also shown by Newton that the Earth is kept in its orbit around the Sun by the attraction of the Sun to the Earth. At the same time, the Earth also attracts the Sun with an equal and opposite force. So remember in the third law of motion that every action, there is an equal and opposite reaction. Newton's law of motions are important because they are the foundation of classical mechanics. One of the main branches of physics, mechanics is the study of how objects move or do not move when forces act upon them.